Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
QuantumLaserPointers.com.
Quantum weirdness and reality. Quantum mechanics is actually poorly named. There is no known or reasonable foreseeable mechanism for quantum mechanics. Quantum mechanics requires communication faster than the speed of light, which is not supposed to be possible, according to relativity. And which is the other really well-trusted theory in physics. Some aspects of quantum mechanics require either correction of the past or prophecy from the past to the present. It's very difficult to test which one of those it would be, because the correction always happens when you're not looking. The latter is equivalent to prophecy from the present to the future, of course, because that means that you simply go back to the past and put yourself there, and now you're prophesying the future, which is a little bit of a trick for us. I'm not going to try to explain all about quantum mechanics. I'm just going to show you some experiments for which there's no good explanation in mechanical terms. There's some people that are trying, but I have not. There's one aspect of it that I think is still giving trouble. I will then try to show you some experiments that appear to be impossible without personal choice in influencing matter and therefore influencing the past. Quantum mechanics doesn't seem to care that much about time. Now, there are two foundations that we're going to be talking about. One of them is the two-slit experiment, where light behaves as if it were waves, and then you get to the end and you have light and dark patches. The only problem with this is that, and this is the kind of thing you come up with, is that these actually don't occur as this kind of barred effect. They actually occur as individual photons hitting specific spots, and the pattern they give you is that kind of a pattern. With electrons, it's pretty easy to see because individual electrons hit a phosphorescent surface. But it's actually true for light as well. If you put a photographic plate in, what you're actually doing is putting crystals of silver chloride or silver iodide or silver bromide, one of the three. And every time one of those little crystals gets hit by a photon, it instantly dissociates into silver and, let's say, chlorine. And when that happens, you have a tiny little silver granule where the light hit. And the next photon hits another one, and the next photon hits another one. And so what you're seeing is a pattern of individual photons there. So the question is, where does it change from particles to waves? Or does it? The problem is that light does act like it's emitted as in particles. It's absorbed as if it came in quanta, according to Einstein, and it scatters electrons as if it came in quanta. Packets that have a definite weight. And electrons are quantum objects as well. So, and they're definitely indivisible. So, the problem is how to make those quanta into waves first and then turn them back into quanta when you need to measure them. The double slit experiment we talked about, light behaves like waves going through two slits with interference fringes, but if you do the same experiment with electrons, they behave like waves going through two slits with interference fringes. Bit on the weird side. When a light or electrons hit the detectors or the screen, now they behave like particles. Where does the change come? Where does light or electron change from a wave into a particle? And that's the hard problem of quantum mechanics. An illustration, electrons are sent through a hole. They give you a pattern like the one on the right here. If you have more detail, they give you a pattern like the one on the left here. Those are all, that's what they call an Airy pattern, and it's typical of a wave. But as you can see, the wave is actually made out of little areas where particles hit the screen and set off a glow. The electrons are going through a small hole. It's characteristic of a wave. In fact, it was originally devised to show that light was waves because light did that kind of thing. That wave is produced even if you let one electron a minute through. And there are ways of measuring how many electrons are going through. And that's the question. How do you change from a particle to a wave? Is it a wave? Is it a particle? And we're going to find things where if you measure certain kinds of things, they behave like waves. If you measure other kinds of things, they behave like particles. And you can predict which one is which, but how mechanically the photon will tell the other photon that's going the other direction, now behave like a wave, now behave like a particle, is really very difficult to do. One of the things about quantum mechanics is you cannot measure two things at exactly the same time to any precision you want. You can measure position, but when you do, you lose track of momentum. You can measure momentum, but when you do, you lose track of position. The double slit experiment is one of the two. The ghost pathway is the other one that is often used to show quantum mechanical effects. And the ghost pathway works like this. You set up a mirror, you set up a light source that will, we can do this now, we can actually give light sources that will put out one photon at a time. An impurity of vanadium and nitrogen in a diamond crystal carbon will do very nicely. We'll send out one photon at a time. And then you send it through a half-silvered mirror, which splits the photon into two. How you split a photon into two is not clear. And then you reflect one back towards the old pathway. You reflect the other one back towards the old pathway. And if you have another half-silvered mirror, rather than being reflected randomly in either direction, which is what you would expect, all of the photons go to the detector that I'm pointing to. The beam interferes with itself at the end, and that's how you know it is in fact a wave and not a particle. But of course, when it's detected by the detector, it behaves like a particle. If the beam is cut down to only one photon, it still interferes with itself. How do you do that? It always goes up, even though there's one photon per minute, let's say, going through. Does the photon go both pathways? Or does it go just one pathway? It acts like it's going both pathways. Well, let's check and find out. So what we're going to do is we're going to take something that's giving us, let's say, 4 counts per second in this. Now, that sounds like a lot, but it means that the first photon is clear through the machine and detected before the second photon ever starts. So it's not two photons going and meeting each other. It's just one photon going both directions. Now what we're going to do is we're going to take one of these and we're going to move it in the way to see whether the photons, are we getting a half a photon going each direction? When we do that, we find that we get 2 of those 4 photons heading in this direction and being counted. But now this photon, these other 2 photons that are going the other way, hit the half-silvered mirror and they get split. One of them will go here, one of them will go here, randomly. We move that counter out of the way, and all of a sudden they all interfere with each other, or with themselves, and all wind up at the top counter. So, well, let's check and move this one in the way. And sure enough, the same thing happens. All of a sudden, the one that's here is now able to be split by the half-silvered mirror. And we get 2 counts here for every 1 count here for every 1 count here. This is behaving more or less classically. But as soon as you move that one out of the way, it goes back to behaving as if the photon split and went both directions. It doesn't matter where in the pathway you do it. Here, here, you get the same result. In fact, one of the things you can do is to take that half-silvered mirror out and see what happens. Now what happens is half of the photons went this pathway and go to that detector. Half of the photons go this pathway and go to this detector. In fact, there's even more sophisticated ways of doing it by rotating the polarization if this is a polarized photon, to where it won't interfere with itself at the end. And you'll get the same effect as if you didn't have, it'll be random, and then when you rotate it back to where it was to begin with, it will interfere with itself. Now, there's something else that you can do with this, and that is you can move this mirror up 1/2 wavelength. And when you do, now everything interferes and goes over here. If you move it up 1/4 of a wavelength, you'll get 2. But you'll actually get this nice sine curve as to which way it goes. It isn't a straight line curve, which is what quantum mechanics predicts and not what standard mechanics would predict. And then you move it another 1/2 wavelength up, and now everything goes to the upper counter instead of the far right counter. That movement is one way of demonstrating that there is, in fact, quantum interference going on, because you get interference there. Einstein realized that quantum mechanics spelled the end of the mechanical universe. He tried hard to disprove Heisenberg's uncertainty principle and failed. He tried to prove that there must be hidden variables that these photons were carrying with them, and that they somehow knew what was going on, and proposed something called the EPR experiment for Einstein, Podolsky, and Rosen. And I'm not going to go into that. We talked about that the last time we were here. Since then, Bell's inequalities, which apply to the EPR experiment, and Leggett's inequalities, which apply to a single set of photons, or photons that are going repeatedly the same way so that you can manipulate them, have been violated by quantum mechanics. Well, quantum mechanics said that they would be violated, and experimental data backs up quantum mechanics and not the common sense way of viewing things, what you would call classical mechanics. But then there's something called quantum erasure, which is even more interesting. Quantum erasure comes in several flavors now, one with causally disconnected choice. You can choose whether to erase or not to erase, and you can choose that literally miles away. And then there's delayed choice quantum entanglement swapping, which means that you can entangle two particles, and two particles that they were entangled with now are entangled with each other, but not with the original ones. And delayed choice quantum eraser. And what the delayed choice means is that you're measuring something, and it now corresponds to what you measured later and how you decided to measure it. And I'm going to show you some experiments, probably the classic ones on both of those. But before we do, I'm going to talk about quantum erasure. Instead of light, we're going to use electrons. It's very clear that electrons are, in fact, particles. You can't have a half electron or a third of an electron. If you could, we could never figure out the weight of an electron. And one of the things you can do is have an electron source, and you can tune that down to very low levels, and you can actually put a detector here and hook it up to something, and when you do that, you can count how many electrons go through, because when an electron goes through, it's moving, it sends out a tiny little magnetic field that you can take a coil and you can actually detect the electron went through at this time. So we have a way of detecting electron without stopping it. Probably slows it a very slight amount, but it doesn't stop it. It keeps it going. So when you divide the beam into two and then you recombine it, I'm being very simplistic about this. There are actually quadrupoles and other things that you do to keep it focused. But basically, you're taking the electron and sending it down two paths, then recombining them. When you do, you get an interference pattern that looks like a wave. Okay? So far, so easy. So good. So now we can check which way the electron went without ever stopping the electron. We're just going to measure two more. We're going to put two more of these little coils, one here and one here. And that way the electrons that go through this pathway have to go past this one, and the electrons that go through this pathway have to go past this one. Now, we could have put these in exactly equivalent positions. It's just that it gets really terrible trying to draw it. So, but the principle is the same. When we do that and we turn on our detectors, we find out that the electron goes one pathway or the other, but not both. And when we do that, our interference pattern disappears. Knowing which way it went means that it couldn't go both ways and give you the pattern. Really bizarre. Well, if we turn off our detectors and leave the coils in place, the electron goes back to interfering with itself. It only does this if you look. And it gets weirder than that. Let's supposing, we've now detecting what we're doing. We're going to take this and we're going to turn off our detectors, and we can even leave one in. Now what we're going to do is we're going to turn on only one detector. And the other one could be there, but we're going to just disable it in some way so that it won't affect the electron path. Now this is kind of weird. Now you see the electron can go this path and be detected, or it can go this path and not be detected, right? And you can, in the detector, you can tell which ones went which way because of their timing. But you never actually looked at the electron that went this way. You just knew that it had to be there because it wasn't here. When you do that, the interference pattern goes away. The interference pattern goes away for the one that went this way. Well, we kind of knew that. But the interference pattern also goes away for the electron that went the way it wasn't being detected. Somehow the electron knows that the path it did not take was being watched. Figure that out.
The information is between the two detectors you have there.
Pardon me?
The information is already received. You know, having 3 detectors is in fact overkill. You only need 2.
That's right. You only need 2, but the 2, you actually only need one.
The combination of those 2 detectors.
You don't even need this one. This is just there to show that one electron went past.
Yeah, but if you only had one, yes, but that one, in combination with the second detector, gives you for all the information you can need to know which path it took.
That's correct.
If you only had one detector on one of the branches, you wouldn't know if there was an electron going through.
That's
Then you wouldn't have the complete information you need that there is an electron coming.
But if you turn this detector off, you still destroy the pattern. The pattern is dependent on knowing that any electron that went through one pathway and not the other. And once you know that, you're done. And the odd thing of it is, you never get a half an electron through this and a half an electron through that. All you get is it's unitary electrons going through.
Might as well get in the wild area. Maybe electrons are more intelligent than we think.
Well, if brains are required for intelligence, then it's hard to see how an electron has a brain.
However,
Are we sure of that?
Either that or maybe somebody with a brain is watching and making sure the experiments come out right. Question way back here.
If we are not detecting the presence of the electron, and it has an interference pattern, can we infer that no intelligence knows whether the electron went one way or the other?
You mean, does God know even though we don't?
Does God affect the interference pattern?
Or does God leave it in an undifferentiated state because he doesn't need to differentiate? He only needs to differentiate if we ask him to.
I get the feeling that quantum mechanics is essentially a conundrum because we do not really understand the connection between information and matter. And once we understand that those are two interdependent, how should I say, properties of what there is, then but we have no intuitive way of relating information and matter at present. You see, we have finally got to the point where we know how to relate energy, matter, space, and time in the E equals mc squared type situation, but that expression is missing information. We don't know how to combine information with the rest, and how that all works together. That to us is still a really fuzzy thing. So
Well, I guess what
I would suggest that these kinds of conundrums would fall out once that critical problem has been addressed.
maybe what I could say is this, that what it suggests is that certain kinds of models of reality that have matter and energy completely separate from information are simply not valid.
That's the issue. Yes.
Question? If we put the detector on and the interference pattern goes away, and then we walk away from the room, is there any way to tell if a non-living detector is affecting the interference pattern?
Well, actually, if we put data recorders on, it's as good as if we were watching.
Yes, because it means that we can look at it later.
Is there any way to tell whether the wave function collapses independent of our observation, but rather it collapses because of the electrons are having an effect on something else, some matter, and then that interaction causes the wave function to collapse?
Well, we're going to be discussing some of that in just a bit. We're going to discuss quantum erasure with causally disconnected choice. That means that we decide whether we erase it or not. But we decide it in some place that's far enough away that light can't get from where we're deciding to where it is. And there's actually an article with that title, and it's found both in Archive and in PNAS, and unfortunately PNAS I can't find the page number for it, but if you Google it you can find it, or if you can go to the Archive article you can find it. And it's not freely available on the web, so this is, I really should have this in the references instead of the one I have, because I think the one I have is in Nature, which is behind a paywall. And the PDF they give isn't as good as the Archive one anyway. No, I take it back. No, this one is in PNAS, and you might be able to get it. But I can tell you that the Archive is just as good. The next one will be behind a paywall. And basically what they're doing is they start out with the lab one, and they have the standard two pathway experiment. And it either goes to detector 1 or detector 2, and they can crawl this up and down in order to shift all of the, if it's interfering, all of the photons to either detector 2 or detector 1, which depending on exactly how far up you are. And they deliberately time delay it by having it go around a couple of coils of, probably several coils of fiber optic cable. In the meantime, they send it to another lab, which in one case is 50 meters away, and then you're going to see that they can actually go further than that. It's amazing what they do with it. And this is a fiber optic cable that's 55 meters long. Apparently it takes an extra 5 meters to get, because you can't make the cable that straight. Probably has to have a little curve in it going around stuff. And that will go to lab 2, where they will either measure the polarization in one plane, which is a horizontal vertical plane, in which case you can tell, because these two photons are entangled, the ones that are going this way and the ones that are going that way, so that if it hits detector 3 and the interference is set up just right, everything will always go to detector you can get everything into detector 1, or detector 4, everything goes to detector 2. That is to say, it always takes the same pathway. If you took the mirror out. Now, when you put the mirror in, when you do that and you know which path it took, because you measured the other photon that went the other way, you lose the interference pattern. On the other hand, if you measure this in a different polarization plane that no longer gives you the clue as to which way the photon went here, it could have gone either way. Now you get an interference pattern that's definitely distinguishable, and they actually have a lab that was putting out quantum noise, which is totally random. If you did this far enough away, you could presumably sit there and flip the switch yourself. Just deciding, oh, I want it on now, off now, on now, off now. Make it completely random. And the switch is done in such a way that light from the switch can't get over to this in time to inform the photon which way it's supposed to go. That's what the future light cone here is supposed to show you, that this event, light from either the quantum decider or the measuring device, can't reach this point fast enough to influence it. So we have what they call a space-like separation. In some frame of reference, it's exactly at the same time. Not in our frame of reference, but in some frames of reference. So now what we're going to do is we're going to turn this on. We're going to randomly decide whether to measure the photon in a way that allows us to tell which way the other one went. When we do that, the results we get, when we know which pathway it took, is really close to random. Now, you can see that there's some error when they do this, and so it's not quite exactly, but it's pretty close. You can kind of imagine that maybe the red ones are up a little bit and the black ones are down a little bit, but that's a really tough call. However, if they do it in such a way that you erase the information as to which way the photon went, now you get very nice interference pattern depending on how you crawl this thing up and down. This is classic, that some of them will go one way and some of them will go the other way. But let's say you pick a 19.5 millimeters, 90+% of them are going to go the red direction and not the black direction. The one detector will get all the noise in the other one, and if you crawl that up a half a wavelength, now everything goes to the black detector. So you get a really nice interference pattern. Now, they repeated this with 144 kilometers between the two laboratories, which means that when they transmit it, they have to actually use a telescope to collect the photon. How they got it to collect that photon and not stray photons that happen to be in from somewhere else, I don't know. And that probably contributes to the fact that the statistics aren't quite as good. But the point of it is that you can go all the way from one island of the Canary Islands to another island, which is pretty close to 100 miles away. And you can do the same experiment. This is a causally separated choice. You can decide in laboratory B whether you want the photon to have interfered with itself or not. It doesn't really matter when you do it. You can do it before, you can do it after, you can do it during the time that it's happening. that isn't weird enough, they've done what they call experimental delayed choice quantum entanglement swapping. And this known is the one that is found in Nature Physics, but you can get the same article in archive.org for free. And in this one, what you do is you have a source that sends two entangled photons, one to what they call Victor and one to Alice, and then this one is sent to Bob and Victor. Alice and Bob just happen to be A and B, fancy ways of saying it. And here you can decide whether to entangle those two photons or measure them separately. If you measure them separately, then photons 1 and 2 are entangled. If you measure them, and photons 3 and 4 are entangled. If you entangle these ones, they stop being entangled with 1 and 4, but now 1 and 4 are entangled with each other. Alice looks at her data and it looks completely random. Bob looks at his data and it looks completely random. When Victor shows them the key, they find out that these correlations either do or do not exist depending what Victor's decided to do. And that's and I'm not sure I can explain that exactly to you how that works there, so I'm not going to try. Although if we've got some quantum mechanics people here, maybe they can. But this is the actual experimental apparatus. They send ultraviolet light through a barium borate crystal. And that has a particular property where it will take the ultraviolet light and split it into two photons, each one having half the frequency. So instead of 414 nanometers length, these ones will be 800 nanometers length, and one goes to Alice, and one goes to Victor, and one goes to Bob, and one goes to Victor. And again, they can coil that up, or they can put Victor a long ways away. It doesn't really matter. And then Victor has this very complicated apparatus that can either entangle them or not, and then measure them at the end. Measure each photon's polarization, and also measure each photon's which detector it went to. And this illustrates the entanglement witness value, which is when it's negative means they're entangled. And in the one case, you have photons 2 and 3 that are entangled. We deliberately did that. And as soon as you do that, photons 1 and 4 are now entangled. Whereas if they are not entangled, if it's separable state measurement by Victor, then what you get is 1 and 2 measured entangled, and 3 and 4 entangled, but not 1 and 2 and 3 or 1 and 4. That's kind of weird, especially when Victor's done his measurements after Alice and Bob have gotten theirs done and all recorded and everything. Then there's what they call a delayed choice quantum eraser, which is actually pretty old. It's 1999, and that can be found on the internet for free as well. And basically they have a setup like this. Now this is incomplete. They should have another detector out here, and in fact I'll show you that in a minute. But the idea is that they put the barium borate here, and the two photons go in slightly different directions. If they don't do any measurement here, and they move this detector up and down, they will find that you have you will have a wave-like pattern in D0. However, if they send these two here, they can determine whether, or the mirror determines whether one photon gets reflected off to detector D3, or the other the other photon is allowed, or the other path for the photon to take, I should say, is to go down to a mirror, be reflected through a half-silvered mirror, and then either wind up with D1 or D2, and when you measure it that way, you can't tell which way it took. And when you do that, you get a D0 giving you an interference pattern. I'm going to show you that in just a minute, because and it doesn't matter whether it's D1 or D2. Well, actually it does. There are two interference patterns that are complementary to each other. Whereas a D3, all you get is that fuzz. And presumably, if you have a detector here at D4, you'd have the same fuzz. This is what you get for the DO positions if you're using detector 1. And you'll notice that you have this wave-like pattern here. Even if nobody drew you the lines, the theoretically correct lines, you could tell that that's wave-like interference pattern. Now, interestingly enough, if you go to detector D2, you have a wave-like pattern as well, but it's waves that are shifted by 90 degrees. So that if you put the two of them together, you get a blob, but if you check either one of them, you actually get an interference pattern. Now, if you measure the photons that go to D0 when you're getting a photon out of D3, you lose the interference pattern. Now, as I said, what you really want to do is you want to have a fourth detector, and of course, if you do that, you're going to wind up with a blob as well. But that experiment's already actually been done. And now you can determine what kind of pattern you get at detector D0 by whether you allow photons to get through and erase which way they went, or whether you allow photons to go out and you check to see which way the other photon went. And as soon as you check which way it went, you destroy the interference pattern. These results seem to require either intelligence in the particles or intelligence guiding the particles. For my book, the particles are too small to have that kind of intelligence, and they're just simply not capable of doing that. They put some strain on the idea that particles are simply reacting to laws. I haven't seen yet a good explanation. I've seen several trials. The distinction between past, future, and absolute elsewhere, or space-like separation, or if you want to call it present, seems to be blurred. If quantum mechanics doesn't seem to pay any attention to when you do which measurements, it still comes out that way. For past-future pairs, this would seem to argue for either someone rewriting history in order to make it fit, or prophecy, that is to say, I'm going to have this one hit over here and this one hit over here, and they're going to be up and down because when it comes time, I'm going to make the other measurements fit the measurements we've already made, or both. And in either case, it raises the question of, can we really be sure that prophecy is not possible? It does kind of sound like maybe it is. And I come back to what Richard Conhenry and Stephen Palmquist said. Richard Conhenry is in the physics department at Johns Hopkins, so respected position, mostly respected physicist, but as you can see, as we go through, his ideas are a little bit hot. Elaine Aspect is the physicist who performed the key experiments that established that if you want a real universe, it must be non-local. Einstein's spooky action at a distance. Aspect commented on new work by his successor in conducting such experiments, Anton Zeilinger, who, by the way, was involved with the first two of those that I gave you, and his colleagues, who have now performed an experiment that suggests that giving up the concept of locality is not sufficient to be consistent with quantum experiments unless certain intuitive features of realism are abandoned. Be clear what is going on here. Quantum mechanics itself is not crying out for such experiments. Quantum mechanics is doing just fine, thank you, having performed flawlessly since inception. No, it is people whose cherished philosophical beliefs are being threatened that cry out, I would say scientific beliefs, because most people don't even think of them as philosophical. They think they're so solid that it isn't even philosophy anymore. Sort of like evolution is a fact, not a theory, you know? It is people with those beliefs that are being threatened that cry out for such experiments, exactly as Einstein used to do, with exactly the same hope, we think in vain, that quantum mechanics can be refined to the point where it requires, or at least allows, belief in the independent reality of the natural world it describes. Quantum mechanics makes no mention of reality. In figure 1, I'm going to just go to real quickly. That's an electron in a particular orbital. Has a bunch of peaks separated by 0. How do you get from peak 1 to peak 2? A little on the bizarre side. Indeed, quantum mechanics proclaims we have no need of that hypothesis. Now we are beginning to see that quantum mechanics might actually exclude any possibility of mind-independent reality, and already does exclude any reality that resembles our usual concept of such. As Aspect said, it implies renouncing the kind of realism I would have liked. Non-local causality is a concept that has never played any role in physics other than in rejection, action at a distance. That can't possibly be. Until Aspect showed in 1981 that the alternative would be the abandonment of the cherished belief in mind-independent reality. Suddenly, spooky action at a distance became the lesser of two evils in the minds of the materialists. Why do peoples cling with such ferocity to belief in a mind-independent reality? It is surely because if there is no such reality, then ultimately, as far as we can know, mind alone exists. And if mind is not a product of real matter, but rather is the creator of the illusion of material reality, which has in fact, despite the materialists, been known to be the case since the discovery of quantum mechanics in 1925, then a theistic view of our existence becomes the only rational alternative to solipsism. But that's my opinion and the evidence for it. Now it's your turn. Go ahead.
So it may be that the answer to my question was there, and I just don't understand it. I mean, is it really minds that determine whether something is particle or wave nature, or could it be simply detectors that we don't normally think of as a mind, but simply matter being interacted upon, that interaction causes it to be particle or wave?
Well, the thing about it is the detectors are put there deliberately by minds. Detectors don't normally just decide by themselves, oh, now I'm going to detect something. First of all, they're made and then they're positioned secondly. And even if we decide that we're going to measure this, if the quantum generator says that, we have to hook it up. And then we have to record it. So in one sense, you're correct in that there is an argument that the measuring device is what causes it to collapse. But what we find out is the measuring device, if you don't collapse the waveform of the measuring device in some way, then we can go back and erase the measuring device, and it will behave as if it's a wave instead of a particle anyway.
So are let's say, chlorophyll, are those measuring devices?
Well, do they collapse waveforms?
That would be the next question. Because we don't normally think, we don't think about chlorophyll being placed there for the purpose of doing a physics experiment.
That'd be an interesting area to explore.
See, chlorophyll is extracting energy, not information.
Well, if it...
Bacteria are for the purpose of extracting information. And when you're taking information out of a system, you're altering the system. You cannot add or subtract information from something without changing it. It doesn't matter who's looking.
Let's see, Ariel, and then we'll go up.
Looking at the last concept you've presented there, one is faced with, at least I am faced with the basic question, is causality real, or am I going to have to throw out rationality? And can they both exist? Is an idea I kind of toy with a little bit, but I'm not completely happy yet that we can throw out causality in spite of these experiments, as it's simply we don't have enough information yet to explain them. But I'm totally unwilling to just throw out all causality. I have to throw out reason if I'm going to do that. Reality doesn't make sense to me. The Bible doesn't make sense to me. The rationality of the Bible, which is, according to a number of historians, the cause of modern science developing in the Western world instead of in Eastern religions and other ancient civilizations that had plenty of time to develop it. It still seems to me that causality, well, I mean, God says you do this, this will happen, so on. He uses causality. There's an awful lot we don't know. We're so happy at times, why does a book fall on the floor when we let go of it? Because the gravity pulls it down, we all know that. We have no idea why gravity pulls it down. But we're happy with these rather superficial cliches, electromagnetic waves and so on. Boy, there's very little we know about those things.
Well, the current theory is that the matter of the Earth warps time-space so that the book which is falling is actually remaining stationary.
Sure, but great.
Thanks for explaining.
Could I just say something real quick? I think it's Proverbs or Ecclesiastes says, a curse causeless shall not come. So even the world of evil is built around cause and effect.
I don't intend to, good morning, to go into any dialogue about this because I want to get to church. But I thought, in case you have not read it or become aware of, Lisa Randall, a physicist at Harvard, she speaks of the what's it I'm trying to say? The warp passages. You might want to make a note of that. And then let's reach back in time to Alfred North Whitehead, his book on science in the modern world. Take a look at his chapter there, Einstein's theory and quantum. So you might want to look at that. And I don't want to go into dialogue about it right now because maybe
Sure,
we can-
I understand.
But I enjoyed very much what you had this morning.
Very good presentation. Enjoyed it. Very thorough. A couple of comments I'd like to make. One on the idea of weirdness itself, and the other question you raised right at the end, what kind of reality would make this sort of weirdness possible? First, weirdness is not a property that things or events possess. It's rather a name that we give to things that are unexpected or that are different from what we're accustomed to.
That's true. The weirdness is in our heads.
But there are.
Nature goes on just fine without us.
Right. But there are two kinds of weirdness. There's just as there are two kinds of ethics. We talk about situational ethics as being things that are right or wrong for particular groups at particular times in particular places, but not universally right or wrong. And there are things that are weird to particular groups at particular times and places, and they're what you might call situational weirdness. And there's absolute weirdness, things that genuinely are different from anything else in the world. They're sui generis.
And that
For
presumably
instance, the singularity from which the Big Bang developed, if you only
most
believe in
cultures
one
would find them
universe,
weird, not just ours.
Right. But from a God's eye point of view, the singularity from which the Big Bang developed, if we have a multiverse, as string theory requires, would be commonplace. Every universe would have arisen from a singularity, and singularities would be probably infinite in number and not at all weird or unique. So the idea of weirdness is strictly a relative. It's not an absolute, except perhaps for singularities. Now, secondly, what kind of a reality will support it? Well, you touched on, I think, the view that's becoming more common at the end. Niels Bohr really started that off with the Copenhagen solution, which is pretty much logical positivism. We stick to what we can observe and measure. Though that's the only thing we really can know anything about. And there's no reason for thinking there is any more to reality than what we can observe and measure. On the other hand, and I think this is a much more plausible view, and it's certainly the one that theists take, and it's the one that Haldane took when he said the world is not only stranger than we think, it's stranger than we can think. And it's the one that Sir James Jeans took at the beginning of the 20th century when he said the more we know about the universe, the less it appears like a great machine and the more it appears like a great mind. And it does seem that information may be the basic stuff of the universe or the ultimate substance of the universe. And in that case, it would be very nearly equivalent to what is traditionally called God. Consciousness or mind, which can call matter into existence. We can certainly do that ourselves when we set up experiments, as you've been discussing, that question nature. And the way we question it determines what reality is at the subatomic level. A universal mind could determine what reality is at the cosmic level.
Yeah, it's kind of weird. We can determine whether an electron went one path or both, just by looking at it. Now, the one thing, we don't have full control. We can't tell you which path it's going to go down. But we do have the ability to say it went down one or the other. And when we do, it has certain consequences. If we decide that if we want it to go down both paths, we just simply stop looking at it and it goes down both paths and gives us our familiar interference fringes. So mind is utmost. Now, let's see, I think we have one comment here and one comment there. Since
so
you got
there's
the mic,
this-
I'll let you go first.
There's this term retrocausality, which I think is maybe postulated to explain how observations now can affect things in the past or maybe even the future. Can you say anything about retrocausality?
Well, if God doesn't have to collapse the waveform until we tell him to, then he can leave things undifferentiated. In which case, if he has something that is technically undifferentiated in the past, And we want to establish something. We can actually establish that at this point we want him to go back and differentiate that.
So are we controlling the past? Does our choices now?
Our choices now, to a certain very small extent, it's not a huge extent. It's not like we can control all of the past or make it all go that way, but we have the ability to differentiate the past. God decides which way it differentiates.
Wow.
It's not your usual way of thinking of things. Certainly materialism doesn't lend itself easily to that kind of a concept.
I'm not happy about that.
Daniel began to pray. God sent an angel to answer his prayer, and he arrived before the end of the prayer.
Was that the one where the angel was sent 3 weeks ago?
Essentially.
And God knew it was going to be a delay here, so we're going to have to start 3 weeks earlier?
Well, reminds me of the letter that Sister White wrote from Australia, in which she wrote precisely the words quoted of conspirators that spoke about it the night before.
So, for those of us who are theists, this concept of God being able to kind of work backwards in time is actually kind of a little bit of a welcome theory. Go ahead, and then we have a comment there. All right. You didn't. I thought you had your hand up.
Are you looking at me again?
Yeah.
No, I didn't. Pantheism says God's everywhere. We like to think he's somewhere. And yet, through the medium of the Holy Spirit, he's here in the room.
So there is a sense in which the pantheists are, if not right, at least half right.
So I don't need no quantum mechanics.
Okay.
Wait. I've been holding this.
Oh,
for a
okay.
while.
I'm sorry.
It seems to me that we have a little bit of a problem of thinking about information separate from a mind. And this is the problem, because we do not at present appreciate the connection between information and matter itself. You see, okay, how do I put it? Let's say that I just get a magnet and I just shake it like this. What am I doing? I'm essentially emitting a light from it, an electromagnetic wave. Can we see it? No, we can't. It is.
But if you get the right detectors, you can see it.
If you had the right detectors, you would be able to see it. However, this is just a magnet that I'm shaking in my hand. You know what I'm saying? The very fact that I am accelerating a magnetic field, I'm generating a perpendicular electric field, which itself will then percolate with further magnetic field, and so essentially I'm emitting a light. But that is very low intensity. Very low intensity. Nothing compared to a laser beam. It's like comparing a firecracker to a nuclear bomb. It's very different. So here we're talking about information on the level of subatomic particles, and we're trying to compare it to information on the level of a mind. The mind harnesses the information and works with it and gets it on a much higher level than it is just the property of whether an electron went this way or that way. Who cares? You know what I'm saying? But such information can be carried on a much larger and a more meaningful level. That is what the mind does. It's a huge issue. But it doesn't mean that we somehow cancel out reality or something. by suddenly realizing that information and matter are interdependent. It means that we need to have a different appreciation for reality than we did before.
I think, therefore I answer.
Go ahead.
I have a mic here. One final comment following up on what I was saying earlier about
And then we'll probably have to close, so you have the last comment.
about the unknowability of reality. Quite apart from whether it gets us into theology, and you need to suppose God in order to explain some of these things like quantum weirdness and the entanglement of mind and matter, apparently. What we believe about reality is based on our ability to observe and measure and experiment with about 5% of it, according to modern physics and cosmology, if you believe in dark matter and dark energy. And we know nothing really about dark matter and dark energy. It's an inferential construct, but we don't have any evidence that would support inferences from it yet. And very possibly the explanation of a lot of quantum weirdness will be found at the level of physics when we know more about dark energy.
Very possible.
Let me just say this. I'd like to remind you, Dr. Kim, try to look up that book for Lisa Randall at Harvard, The Warp Passages. And then I reference all of this from the Bible and look at Peter and Peter. 1,000 years to God is a day. A day is 1,000 years. And if you wrap your mind around that, put it in your hologram, and equate it to some of these things that we're talking about. Just look to the Bible. Let's go to Cosmo. Let's look in our Bible. And you will soon see we have a book coming, soon, very soon, called Space Age Interpretation of the Bible.
I'll be interested when it comes out. We might even review it here.
Wouldn't that be wonderful? It's already been reviewed.
Okay.
So have a blessed Sabbath.
So next week, orb spiders are not related to each other. Figure that one out. Do that one electron a minute through. And there are ways of measuring how many electrons are going through. And that's the question. How do you change from a particle to a wave? Is it a wave? Is it a particle? And we're gonna find things where if you measure certain kinds of things, they behave like waves. If you measure other kinds of things, they behave like particles. And you can predict which one is which, but how mechanically the photon will tell the other photon that's going the other direction, now behave like a wave, now behave like a particle, is really very difficult to do. One of the things about quantum mechanics is you cannot measure two things at exactly the same time to any precision you want. You can measure position, but when you do, you lose track of momentum. You can measure momentum, but when you do, you lose track of position. The double slit experiment is one of the two. The ghost pathway is the other one that is often used to show quantum mechanical effects. And the ghost pathway works like this. You set up a mirror, you set up a light source that will, we can do this now, we can actually give light sources that will put out one photon at a time. An impurity of vanadium and nitrogen in a diamond crystal carbon will do very nicely. We'll send out one photon at a time. And then you send it through a half-silvered mirror, which splits the photon into two. How you split a photon into two is not clear. And then you reflect one back towards the old pathway. You reflect the other one back towards the old pathway. And if you have another half-silvered mirror, rather than being reflected randomly in either direction, which is what you would expect, all of the photons go to...
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
QuantumLaserPointers.com.
Quantum weirdness and reality. Quantum mechanics is actually poorly named. There is no known or reasonable foreseeable mechanism for quantum mechanics. Quantum mechanics requires communication faster than the speed of light, which is not supposed to be possible, according to relativity, and which is the other really well-trusted theory in physics. Some aspects of quantum mechanics require either correction of the past or prophecy from the past to the present. It's very difficult to test which one of those it would be, because the correction always happens when you're not looking. The latter is equivalent to prophecy from the present to the future, of course, because that means that you simply go back to the past and put yourself there, and now you're prophesying the future, which is a little bit of a trick for us. I'm not going to try to explain all about quantum mechanics. I'm just going to show you some experiments for which there's no good explanation in mechanical terms. There's some people that are trying, but I have not. There's one aspect of it that I think is still giving trouble. I will then try to show you some experiments that appear to be impossible without personal choice in influencing matter and therefore influencing the past. Quantum mechanics doesn't seem to care that much about time. Now, there are two foundations that we're going to be talking about. One of them is the two-slit experiment, where light behaves as if it were waves, and then you get to the end and you have light and dark patches. The only problem with this is that, and this is the kind of thing you come up with, is that these actually don't occur as this kind of barred effect. They actually occur as individual photons hitting specific spots, and the pattern they give you is that kind of a pattern. With electrons, it's pretty easy to see because individual electrons hit a phosphorescent surface. But it's actually true for light as well. If you put a photographic plate in, what you're actually doing is putting crystals of silver chloride or silver iodide or silver bromide, one of the three. And every time one of those little crystals gets hit by a photon, it instantly dissociates into silver and, let's say, chlorine. And when that happens, you have a tiny little silver granule where the light hit. And the next photon hits another one, and the next photon hits another one. And so what you're seeing is a pattern of individual photons there. So the question is, where does it change from particles to waves? Or does it? The problem is that light does act like it's emitted as in quanta, in particles. It's absorbed as if it came in quanta, according to Einstein, and it scatters electrons as if it came in quanta. Packets that have a definite weight. And electrons are quantum objects as well. So and they're definitely indivisible. So the problem is how to make those quanta into waves first and then turn them back into quanta when you need to measure them. The double slit experiment we talked about, light behaves like waves going through two slits with interference fringes, but if you do the same experiment with electrons, they behave like waves going through two slits with interference fringes. Bit on the weird side. When a light or electrons hit the detectors or the screen, now they behave like particles. Where does the change come? Where does light or electron change from a wave into a particle? And that's the hard problem of quantum mechanics. An illustration, electrons are sent through a hole. They give you a pattern like the one on the right here. If you have more detail, they give you a pattern like the one on the left here. Those are all, that's what they call an Airy pattern, and it's typical of a wave. But as you can see, the wave is actually made out of little areas where particles hit the screen and set off a glow. The electrons are going through a small hole. It's characteristic of a wave. In fact, it was originally devised to show that light was waves because light did that kind of thing. That wave is produced even if you use the detector that I'm pointing to. The beam interferes with itself at the end, and that's how you know it is in fact a wave and not a particle. But of course, when it's detected by the detector, it behaves like a particle. If the beam is cut down to only one photon, it still interferes with itself. How do you do that? It always goes up, even though there's one photon per minute, let's say, going through. Does the photon go both pathways? Or does it go just one pathway? It acts like it's going both pathways. Well, let's check and find out. So what we're going to do is we're going to take something that's giving us, let's say, 4 counts per second in this. Now, that sounds like a lot, but it means that the first photon is clear through the machine and detected before the second photon ever starts. So it's not 2 photons going and meeting each other. It's just one photon going both directions. Now what we're going to do is we're going to take one of these and we're going to move it in the way to see whether the photons, are we getting a half a photon going each direction? When we do that, we find that we get 2 of those 4 photons heading in this direction and being counted. But now this photon, these other 2 photons that are going the other way, hit the half-silvered mirror and they get split. One of them will go here, one of them will go here, randomly. We move that counter out of the way and all of a sudden they all interfere with each other or with themselves and all wind up at the top counter. So, well, let's check and move this one in the way.